Right now, as you are watching this, two very different earthquake stories are being folded into one frightening picture. In Northern California, a magnitude 5.6 earthquake struck near Redwood Valley in Willits, shaking a wide part of the state, knocking items from shelves, cutting power to thousands of customers, and producing a sequence of smaller earthquakes that kept people checking their phones. Then, while most cameras were still pointed at California, a magnitude 5.5 earthquake struck beneath the Pacific Ocean about 218 kilometers west of Bandon, Oregon. That offshore event was followed in the same general area by a magnitude 3.9 and a magnitude 3.4. Other offshore Oregon earthquakes had already occurred earlier in the year, including a magnitude 6.0 event that the United States Geological Survey identified as the potential main shock of a 13-event sequence. And more distant ridge swarms had appeared west of Washington. On a map, the dots look as if the entire edge of North America is lighting up at once. But maps can hide as much as they reveal. The California sequence and the offshore events did not occur on one continuous fault. The offshore earthquakes were not automatically on the Cascadia megathrust. And a magnitude 5.5 is not bigger than a magnitude 5.6. The larger story is the tectonic machinery beneath the ocean, where several plate boundaries sit close together and where the most dangerous fault is often the quietest one. Today we are going to break down exactly what happened, what scientists can and cannot connect, why earthquakes far offshore can look more alarming than they are, and what signals would actually make experts more concerned. No guessing, no dramatizing, just the facts, the science, and the real stakes. Drop a comment right now. Have you ever personally felt an earthquake? Even a small one? Tell me where you were and what the shaking felt like. If you want to be the first to know every time something major happens, subscribe. It is completely free. A thumbs up also helps enormously. Let us go for 5,000 likes on this one so the algorithm actually shows it to people who need to see it. Now, let us get into it. The California story began on the morning of June 24th, 2026. At approximately 8:10 in the morning local time, the ground moved near Redwood Valley in Mendocino County. The main earthquake was measured at magnitude 5.6 and was shallow, roughly 8 kilometers beneath the surface. That combination matters. A moderate earthquake close to the surface can produce sharp, damaging motion near the epicenter, even when its magnitude is far below the giant earthquakes that dominate history books. People across Northern California reported a sudden jolt followed by rolling movement. Store shelves emptied onto floors. Wall coverings cracked. Schools and businesses paused operations while staff checked buildings. More than 7,400 customers lost electrical service, and the shaking was felt far beyond Mendocino County. The United States Geological Survey estimated that about 80,000 people experienced moderate to very strong shaking, while millions more experienced weak or light motion. The earthquake was associated with the Macama Fault System, a major strand within the broad northern San Andreas fault network. The Macama is not the famous straight line people imagine when they hear the word San Andreas. Northern California is a complicated zone in which plate motion is divided among several faults. Some are mapped clearly at the surface. Others branch, step, overlap, and disappear beneath sediment or vegetation. When a fault segment slips, the energy radiates outward as seismic waves. The first waves move fastest and usually feel like a quick push. The later shear and surface waves often produce the stronger side-to-side or rolling motion that people remember. Because the earthquake was close to populated areas, phones sounded, people felt it, cameras captured the aftermath, and news coverage expanded immediately. The sequence count also changed as analysts reviewed the data. Early reports described dozens of earthquakes around the main shock. One widely cited report said the United States Geological Survey had identified 44 events in the sequence at that stage. Other public maps showed higher totals when smaller events, wider search areas, or longer time windows were included. That is normal. An earthquake catalog is not a frozen scoreboard. Automatic systems detect events within seconds, but seismologists later relocate them, revise magnitudes, merge duplicate solutions, reject noise, and add smaller events that were missed in real time. This is one reason headlines may say 40, 80, or more than 100 earthquakes while referring to roughly the same period. The difference is often the magnitude cutoff and the shape of the search box, not a secret wave of earthquakes hidden from the public. Scientifically, the Redwood Valley activity was primarily a main shock-aftershock sequence, not a classic swarm. That distinction is important. Aftershocks occur after a larger main shock and generally decrease in number with time as the crust readjusts to the stress change caused by the rupture. A swarm usually contains many earthquakes without one clearly dominant main shock. In real data, the boundary is not always perfect, but the California sequence had an obvious largest event. Calling every cluster a swarm may sound dramatic, yet it can blur the mechanism scientists are trying to understand. 5 days later, at 11:35 Universal Time on June 29th, another strong dot appeared on earthquake maps. This one was far offshore. The United States Geological Survey measured it at magnitude 5.5 at a depth of about 10 kilometers, roughly 218 kilometers west of Bandon, Oregon. Only a small number of people reported feeling it because the epicenter was so distant from land. The National Tsunami Warning Center said a tsunami was not expected. Then a magnitude 3.9 appeared in the same broad offshore area, followed by a magnitude 3.4. To someone scrolling through a global map, the pattern looked like escalation. California had just moved. Now the ocean west of Oregon was moving. The phrase earthquake swarm spread quickly. But here is the first major correction. The magnitude 5.5 offshore earthquake was not larger than the magnitude 5.6 California earthquake. Magnitude is logarithmic. A difference of 1/10 may look tiny, but the magnitude 5.6 released roughly 40% more energy than the 5.5. The offshore story was bigger in geographic and tectonic context, not in the size of that individual earthquake. It occurred within a broad oceanic plate boundary system that stretches hundreds of kilometers and contains several different faults. That distinction changes the risk calculation completely. The June 29th earthquake occurred near the Blanco Fracture Zone, a long transform fault system west of Oregon. A transform boundary is a place where plates slide horizontally past one another. Imagine two heavy slabs moving in opposite directions along a rough seam. The edges lock temporarily. Stress builds. Then part of the seam slips. This is strike-slip faulting. The motion is mainly sideways. The Blanco system connects spreading centers associated with the Juan de Fuca and Gorda plates, and it is one of the most seismically active parts of the northeastern Pacific. Earthquakes there are not rare. Moderate and strong events have occurred repeatedly, including a magnitude 6.3 in August 2019 and a magnitude 5.8 sequence in December 2021. The Blanco Fracture Zone is offshore, but it is not the same structure as the Cascadia Subduction Zone. This is the single most important point in the entire story. Cascadia lies closer to the continental margin, where the Juan de Fuca plate is being pushed beneath the North American plate. It is a megathrust boundary. The Blanco zone lies farther west and accommodates mostly horizontal motion between oceanic plates. One system slides sideways. The other pushes one plate beneath another. Their earthquakes have different focal mechanisms, different rupture geometries, and different tsunami potential. To put that in context, a tsunami usually requires a large volume of seawater to be displaced vertically. A powerful thrust earthquake can lift or drop a broad section of seafloor, moving the ocean above it. A strike-slip earthquake mainly moves the seafloor sideways. Large strike-slip events can still generate local waves through complicated seafloor motion or submarine landslides, but they are much less efficient tsunami generators than great megathrust earthquakes. That is why an earthquake can be strong, shallow, and offshore, while producing no tsunami warning for the coast. The distance also mattered. 218 kilometers is about 135 miles. Between the epicenter and Oregon's populated shoreline lay a vast stretch of ocean. Seismic waves weakened as they spread. The earthquake did not occur beneath Bandon, Coos Bay, or Newport. It was not a hidden coastal rupture directly below communities. Several residents may have felt a faint motion, but the event produced no reported destructive shaking on land. The quiet response was not negligence. It reflected the earthquake's location, mechanism, and measured effects. Still, the offshore sequence deserved attention because it was not isolated from the region's recent pattern. On January 16, 2026, a magnitude 6.0 earthquake struck off the Oregon coast. The United States Geological Survey later grouped 13 events into that sequence. On April 12th, a cluster of approximately 18 small earthquakes occurred near the Juan de Fuca Ridge, about 240 miles west of Westport, Washington. Seismologists with the Pacific Northwest Seismic Network explained that the ridge swarm posed no danger to people on land. On June 3rd, another magnitude 5.7 occurred off southern Oregon. Then came the June 29th magnitude 5.5 and its nearby smaller events. On August 3rd, a magnitude 4.0 was again recorded far off Oregon. Seen one by one, these events are routine products of active oceanic plate boundaries. Seen together on a compressed timeline, they create an understandable question. Is pressure moving toward Cascadia? Scientists ask versions of that question too, but they do not answer it by counting red circles on a public map. They examine the fault mechanism, exact location, depth, waveform, aftershock distribution, stress transfer, and whether the activity is statistically unusual compared with decades of background seismicity. Here is the part nobody should skip. Earthquakes can transfer stress to nearby faults, but the effect falls rapidly with distance and depends on fault orientation. A rupture does not send a simple wave of pressure marching predictably toward the next fault. Some nearby patches are brought slightly closer to failure. Others are moved farther from failure. Many experience a stress change too small to matter. Dynamic seismic waves can trigger small earthquakes far away in regions already close to failure, especially geothermal or volcanic areas, but that does not mean a chain reaction of major earthquakes is underway. The Blanco Fracture Zone has been producing earthquakes for as long as modern instruments have monitored it. Its motion is part of the normal deformation of the Pacific, Juan de Fuca, and Gorda plate system. If every moderate Blanco earthquake were a reliable warning that Cascadia was about to rupture, scientists would have observed that relationship repeatedly. They have not. There is currently no scientific evidence that the June or August offshore Oregon earthquakes were foreshocks to a Cascadia magnitude 9 event, and there is no accepted method that can predict the date, location, and magnitude of a major earthquake. The United States Geological Survey is explicit. Scientists can estimate probabilities over years or decades, but they cannot issue deterministic earthquake predictions. That does not make the offshore activity meaningless. It makes the meaning more precise. The earthquakes confirm that the surrounding plate system is active. They provide data on how oceanic faults release stress. They help scientists refine plate motion models. They test seismic networks and tsunami decision systems. And they remind people that several kinds of earthquakes can occur in the Pacific Northwest, not just the famous magnitude 9 scenario. There are three major earthquake sources that matter to this region. The first is the offshore megathrust, Cascadia itself. The second is deep intraslab earthquakes within the descending Juan de Fuca plate, similar to the magnitude 6.8 Nisqually earthquake in 2001. The third is shallow crustal faults beneath or near populated areas, including faults around Puget Sound and Portland. The United States Geological Survey's 2025 assessment estimated an 85% chance of a magnitude 6.5 or larger deep earthquake in the Puget Sound region during the next 50 years, a 17% chance of a magnitude 6.5 or larger shallow crustal earthquake there, and a 10 to 15% chance of an approximately magnitude 9 Cascadia earthquake during the same period. Those are probability estimates, not countdown clocks. The largest hazard does not always produce the most daily earthquakes. Cascadia is dangerous precisely because the locked part of the plate boundary is often quiet. The fault extends roughly 1,200 kilometers, or about 750 miles, from northern California to southern Canada. The Juan de Fuca plate moves toward and beneath North America at roughly 40 millimeters, or about 1.6 inches, per year. Much of that motion is not released smoothly. The plates are locked along portions of the boundary, so elastic strain accumulates in the overlying continent. Coastal land is slowly deformed. Satellite measurements capture movement over years. Episodic tremor and slow slip occur deeper on the interface. Yet the shallow locked zone may remain nearly silent until a great rupture. The last full margin Cascadia earthquake occurred on January 26, 1700. It was close to magnitude 9. There were no modern instruments in the Pacific Northwest, but forests died when coastal land dropped. Tsunami deposits were left in marshes. Indigenous oral histories preserved accounts of the event, and a tsunami crossed the Pacific and was recorded in Japan without a locally felt earthquake. Scientists later connected these clues and reconstructed the source. Geological evidence indicates that large or great Cascadia earthquakes have occurred repeatedly, with average intervals measured in centuries. But an average is not a schedule. A fault with a 500-year average can rupture after a much shorter interval or remain quiet much longer. This is why the word overdue can be misleading. A fault is not a library book. It does not pass a fixed deadline and become certain to rupture tomorrow. Probability increases or decreases depending on the statistical model and the history used, but the exact timing remains unknowable. Cascadia could remain quiet for decades. It could rupture sooner. Both statements are scientifically possible. The responsible response is not panic. It is long-term preparation. Now compare the human experience of the California earthquake with the offshore Oregon event. In Redwood Valley and Willits, the earthquake was smaller than the disasters people imagine, yet it was close enough to interrupt ordinary life within seconds. Power failed. Objects fell. People moved away from windows. Schools checked classrooms. Hospitals inspected equipment. The shaking became personal because it entered homes and businesses. Offshore Oregon, the earthquake released a similar amount of energy, but distance and fault geometry kept most of that energy away from people. One event became a lived emergency. The other became a map symbol and a scientific question. These are not just geological events. They are human experiences shaped by where the rupture happens, how deep it is, what kind of ground lies above it, how buildings were constructed, and whether people know what to do. A magnitude number alone cannot describe impact. A shallow magnitude 5 beneath a vulnerable town can be more damaging than a magnitude 6 far offshore. A magnitude 7 strike-slip earthquake may cause violent local shaking but little tsunami. A magnitude 9 megathrust can shake an entire region for several minutes and push a wall of water toward the coast. Context is everything. Preparation also changes outcomes. In a strong earthquake, the safest immediate action for most people indoors is drop, cover, and hold on. Drop to your hands and knees before the shaking knocks you down. Cover your head and neck beneath a sturdy table if one is nearby. Hold on so the cover does not move away. Do not run outside while glass, bricks, signs, and building pieces may be falling. At the coast, the rule changes after the shaking. If the shaking is strong or lasts a long time, move inland or to high ground as soon as you can safely move. Do not wait for a phone alert if the natural warning is unmistakable. A local Cascadia tsunami could arrive within minutes in some locations. The way alerts appear can also distort the comparison. California sits beneath one of the densest seismic networks in the world. A moderate earthquake near a city can be located by many nearby stations, checked against felt reports, processed by Shake Alert, and displayed with a detailed intensity map within minutes. Far offshore, the first solution may come from a smaller number of stations at greater distances. A preliminary magnitude can move upward or downward as additional waveforms are reviewed. A location can shift by several kilometers. The public often sees each revision as a new development, even when scientists are simply improving the same event record. A changed number does not mean the earthquake changed after it happened. It means the measurement became more accurate. There is also a basic scale problem in online maps. A map zoomed out to show California, Oregon, Washington, and the adjacent Pacific may place earthquakes hundreds of kilometers apart, almost on top of one another. The eye connects them before the science does. When the map is enlarged, one cluster may lie on a continental strike-slip fault, another on an oceanic transform, another at a spreading ridge, and another within the descending slab. The dots share a coastline, but not necessarily a cause. To demonstrate a connection, researchers need more than timing. They need a plausible stress interaction, compatible fault orientation, and a pattern that exceeds normal coincidence in an already active region. Magnitude comparisons create a similar illusion. The number is not a direct measurement of how dangerous an earthquake felt. It estimates the size of the source. Shaking intensity depends on distance, depth, rupture direction, soil, and construction. That is why the 5.6 in California produced disruption while the 5.5 offshore did not. The energy releases were comparable, but the exposure was completely different. Hazard is the physical event. Risk is the event combined with people, buildings, and systems in its path. The offshore events also expose a monitoring challenge. Earthquakes beneath the ocean are harder to locate precisely than earthquakes surrounded by land stations. Most seismic sensors sit on shore. When an event occurs hundreds of kilometers out at sea, waves reach the network from a narrower range of directions. Location and depth estimates may be revised as more data arrive. Seafloor instruments, hydrophones, pressure sensors, and cabled observatories can improve coverage, but the ocean remains less densely instrumented than California's urban fault systems. This means small offshore events are often undercounted compared with similar events on land. That is another reason the phrase much bigger swarm requires caution. If the comparison is based on public catalog dots, the California network may detect many tiny earthquakes that offshore networks cannot see. If the comparison is based on magnitude, the California main shock was slightly larger than the June 29th Oregon main shock. If the comparison is based on the physical size of the fault system, the offshore plate boundaries are vastly larger. The headline compresses 3 different meanings of bigger into one phrase. The science separates them again. What would scientists watch for next? First, a clear increase in earthquake rate above the long-term background for the specific offshore zone. 1 isolated magnitude, 4 after weeks of quiet, means something different from hundreds of tightly clustered events in hours. Second, migration. If hypocenters move systematically along a fault or upward through the crust, that pattern can reveal changing stress or fluid movement. Third, magnitude progression. Most sequences decay. A pattern of increasingly large events would demand closer analysis, although it still would not provide a prediction. Fourth, focal mechanisms. Sideways strike-slip motion on Blanco carries different implications from shallow thrust motion on the Cascadia interface. Fifth, geodetic change. Global positioning stations and seafloor instruments can detect whether the plates are deforming differently from normal. Sixth, tsunami observations. Pressure sensors and tide gauges reveal whether the seafloor displaced enough water to create a wave. Scientists would also compare the sequence with known behavior. The Blanco Fracture Zone commonly produces clusters of moderate earthquakes. The Juan de Fuca Ridge produces volcanic and tectonic swarms as new oceanic crust forms. The Gorda Plate is internally deformed and generates frequent earthquakes. The Mendocino Triple Junction near Northern California is one of the most complex tectonic regions in North America. A new cluster must be measured against those noisy backgrounds. Unusual does not mean unprecedented, and unprecedented does not automatically mean catastrophic. Keep an eye on official earthquake sequence pages, too. The United States Geological Survey now publishes sequence products that group related events and update their interpretation. These products help distinguish a main shock-aftershock pattern from a swarm and communicate the expected decay. But even official catalogs remain provisional. Magnitudes can move by a tenth. Depths can change. Event counts can rise as analysts lower the detection threshold. Responsible reporting should treat the first number as preliminary, not permanent. The most alarming online claim is that offshore Oregon earthquakes are opening or unlocking Cascadia. There is no evidence that the recent magnitude 5 events have done that. Faults are not doors with one hinge. Cascadia is a huge, segmented, three-dimensional interface. Its locked zone is loaded by plate convergence over centuries. A moderate transform earthquake far west of the megathrust releases stress on its own fault patch. It does not release the accumulated strain on Cascadia, and it does not prove that Cascadia is about to fail. The opposite claim is also wrong. That offshore earthquakes do not matter because they are common. Common hazards can still be dangerous. A larger Blanco earthquake could be felt strongly on the coast. A submarine landslide could create a local wave. An earthquake closer to the continental margin could have different consequences. And the broader region remains exposed to the independent Cascadia hazard, whether or not a visible swarm is occurring. Ignoring the map is no more scientific than panicking over it. The realistic future risk picture is layered. In the short term, the most likely outcome after a moderate offshore event is additional smaller earthquakes that decrease with time. Another magnitude 5 or even magnitude 6 is possible in this active oceanic region, but no one can say when. In the medium term, earthquake monitoring will continue to reveal clusters on the Blanco, Gorda, and Juan de Fuca systems. Most will remain far from land and cause no damage. In the long term, the Pacific Northwest must prepare for deep, crustal, and megathrust earthquakes whose probabilities are measured over decades, not news cycles. For households, that means securing tall furniture, water heaters, televisions, and heavy objects that can fall. It means keeping shoes and a flashlight near the bed because broken glass and power loss are common after shaking. It means having water, food, medication, batteries, and a way to receive emergency information. For coastal residents and visitors, it means knowing the nearest tsunami evacuation route before an earthquake happens. A beautiful beach can become a dangerous decision point if someone waits for confirmation after strong, prolonged shaking. For communities, the work is larger. Bridges, hospitals, schools, ports, fuel systems, water networks, and communications must be designed or upgraded for long-duration shaking. Tsunami routes need signs that remain visible in darkness and bad weather. Vertical evacuation structures may be necessary where high ground is too far away. Emergency plans must assume that roads, power, and cellular networks will fail at the same time. The warning from offshore earthquakes is not that disaster begins tonight. It is that the region's geology never stopped moving while infrastructure and preparedness often moved too slowly. So, did a much bigger earthquake swarm begin offshore while everyone watched California? The evidence supports a more careful answer. A magnitude 5.5 earthquake and smaller nearby events occurred far west of Oregon 5 days after the magnitude 5.6 Redwood Valley earthquake. Other offshore sequences had occurred earlier in the year, including a magnitude 6.0 sequence and a small ridge swarm west of Washington. Together, they show active oceanic plate boundaries. But the events do not form one proven, connected megaswarm. The June offshore main shock was slightly smaller than the California main shock, and there is no scientific evidence that these events were the opening stage of a Cascadia rupture. The title's real warning is not the cluster of red dots. It is the quiet fault east of many of them. Cascadia does not need an obvious swarm to remain dangerous. Its hazard comes from centuries of plate convergence, a long locked interface, vulnerable coastlines, and the certainty that large earthquakes will happen again even though their timing cannot be predicted. The most realistic danger is not a secret chain reaction visible on a phone map. It is people mistaking normal offshore seismicity for either an immediate apocalypse or a reason to ignore preparation completely. No, the offshore earthquakes do not mean a magnitude 9 is beginning. No, scientists have not detected a countdown. But the Pacific Northwest is earthquake country every day, including the quiet days. Learn the fault difference. Know your evacuation route. Secure the things that can fall. Practice drop, cover, and hold on. And And when a headline says swarm, ask whether the data show a true swarm, an aftershock sequence, or several unrelated events plotted close together on a very large map. Now I want to hear your story. Have you ever felt the floor move, watched lights swing, or heard a building creak during an earthquake? Tell me where you were and what you did in those first few seconds. If this breakdown helped separate the real hazard from the viral fear, press the like button and help us reach that 5,000 like goal. Subscribe for calm, evidence-based coverage every time the planet changes fast. No filler, no guessing, just the facts and the full picture. Let us go. See you in the next one.